comparison of EMFs. Comparison of EMFs of two electric cells. Comparison of EMFs of two electric cells using potentiometer. Now we can draw the diagram of a potentiometer containing a driving battery, an ammeter and rheostat. This is the driving battery of E.m.f. E'. This is the driving battery of E.m.f. E', driving battery, which drives the potentiometer or the circuit. And to this driving battery of E.m.f. E', an ammeter will be connected in series combination, and we can denote positive and negative terminal. This is the negative terminal which is connected to negative pole of the battery, and we can denote positive terminal of the ammeter. This ammeter measures the magnitude of current, and this ammeter is connected to a rheostat. RH is the rheostat or variable resistance. This is what a rheostat or variable resistance which is used to control the magnitude of current. And we can connect a key. And a plug will be inserted to generate the current from the driving battery. And there are two terminals, A and B, and between A and B a potentiometer wire is connected. This is the potentiometer wire, which is made of constantan or manganese, having 0 temperature coefficient of resistance. AB is the potentiometer wire. A plug is inserted in the key K. In that case, current will be generated from the driving battery, and this is the rheostat. If the rheostat is connected to that point, then effective area will be what you know. Effective area will be this one, and we have to consider resistance of that part. Now again the rheostat is connected to that point, and effective area will be this part. I is the current which is generated from the positive pole of the driving battery of E.m.f. E'. Now we can connect two electric cells as shown in the figure. This is the electric cell. This is the first electric cell of E.m.f. E1. We can connect another electric cell, and here and this electric cell of E.m.f. E1 and other electric cell of E.m.f. E2 will be connected to the terminal 1 and 2 of two-way key. Second electric cell has the E.m.f. E2, and the common terminal of the two-way key is 3, is denoted by 3. The common terminal of two-way key is denoted by 3. This is the two-way key. Two-way key having 3 terminals. To the terminal 1 and 2, two electric cells are connected, and this is the two-way key. This is the two-way key. Two-way key. The second cell has the E.m.f. E2. Second cell has the E.m.f. E2. Second cell has the E.m.f. E2. The common terminal of the two-way key, that is the terminal 3 of two-way key, is connected to the jockey J through a galvanometer G. The common terminal, that is the terminal 3 of two-way key, is connected to jockey J through a galvanometer G. And if a plug is inserted between 1 and 3, in that case I prime will be the current which will be flowing through the cell of E.m.f. E1, and that current I prime also flows through the galvanometer G, and it will uh, flow through the jockey, and it will be flowing again through the potentiometer wire AB. When the jockey J is pressed with the point C1 of potentiometer wire, and the point C1 is at a distance L1 from the end A of potentiometer wire, and also we can assume that E1 is greater than E2. The jockey J is pressed when the jockey J is pressed with the point C1 of potentiometer wire AB, the galvanometer G shows no deflection. Galvanometer G shows no deflection. The galvanometer G shows no deflection, and no current will pass through the branch containing the cell E1. This is the balance condition. When the galvanometer shows no deflection, in that case no current will pass through the arm AE1J. If the plug is removed between the terminals 1 and 3, and the same plug is inserted between the terminals 2 and 3 of two-way key, a current I will be flowing, a current I double prime will be flowing through the arm AE2J, through the arm AE2J. In that case, when the plug is inserted between the terminals 2 and 3, the jockey J will be pressed or will be touched with the point C2 of the potentiometer wire, and the point C2 is at a distance L2 from the terminal A of the potentiometer wire. The positive terminals of both the electric cells of E.m.f, E1 and E2 are connected to the point A, of the potentiometer wire AB. The positive terminal of the cell of E.m.f E1 and the positive terminal of cell E2 are connected to the terminal or to the point A of the potentiometer wire. This positive terminal of E1 and E2 are connected to the point A of the potentiometer wire. Also, we can say that the negative terminals of the two electric cells of E.m.fs E1 and E2, the negative terminals of the electric cells of E.m.fs E1 and E2 are also connected to the terminals 1 and 2 of the two-way key. Negative terminals of the electric cells of E.m.fs E1 and E2 are connected to the terminals 1 and 2 of two-way key, while its common terminal 3 is connected to the jockey through a galvanometer G. The common terminal 3 of two-way key is connected to the jockey J through a galvanometer G, as shown in the figure. When the plug is inserted in the gap between the terminals 1 and 3 of the two-way key, when the plug is inserted in the gap between the terminals 1 and 3 of two-way key, so that the electric cell of E.m.f E1 comes in the circuit, Now the jockey J is adjusted at different points of the potentiometer were between the two terminals A and B. Now the jockey J is adjusted at the different points of the potentiometer where AB. Different points of the potentiometer where AB for which the galvanometer G shows deflection. But if the jockey J is pressed with the point C1 of potentiometer where AB, the galvanometer shows no deflection. The galvanometer under bracket G shows no deflection and no current flows through the arm AE1C1 through the arm AE1C1. Now through the arm AE1C1 current is I minus I1. I minus I1 is the current which is flowing through the arm AE1C1. If the jockey J is touched with the point C1, galvanometer G shows no deflection and no current. That means I minus I1 will be 0. No current will flow through the arm AE1C1. Now we can denote the potential at the point A as VA. Potential at the point A is as VA. Now we can denote that the current I minus I1 which is equal to 0 that will flow through the arm AE1C1. Therefore, potential at the point A. Therefore, potential of the point A. Therefore, potential of the point A will be equal to the potential of the positive terminal of the electric cell of E.m.f. E1. Potential of positive terminal of the cell of E.m.f. E1. Here we consider no current flows through the resistance, and V and Vp are the potentials. R is the resistance of this portion. Va minus Vp equal I dot R. Now as I is equal to 0, Va minus Vp is 0. That's why Va equal Vp. That means if no current flows through a arm, in that case potential at the two terminals of that portion will be equal. In this case we can denote the potential at A as Va and potential at the point C1 as Vc1. Now no current flows through this arm AE1C1. That's why I minus I1 will be equal 0. I minus I1 will be equal 0. Similarly, potential of the point C1 is equal to potential of the negative terminal of the cell of E.m.f. E2, cell of E.m.f. E1. Therefore, potential of A minus potential of the point C1, potential of the point A minus potential of the point C1 equal to potential of positive terminal of the cell of E.m.f. E1 minus potential of negative terminal of the cell of E.m.f. E1. Left hand side it should be potential of the point A minus potential of the point C. Potential of the point A subtracting potential of the point A minus potential of the point C1. And on the right hand side we can subtract potential of the negative terminal from the potential of the positive terminal of the cell of E.m.f. E1, or comma Va minus Vc1 will be equal to the terminal voltage of the electric cell of EMF E1. Terminal voltage of the electric cell of EMF E1 or comma VAC1 is equal to terminal voltage of the cell E1 is equal to E1 minus I1 into R1. I minus I1 into R1, where I1 is the current flowing through the portion AC1 and I minus I1 is the current flowing through the cell of EMF E1. I minus I1 is the current which is flowing through the arm AE1C1. I minus I1 is the current. Now the terminal voltage of the cell E1 and internal resistance R1 is V1, which is equal E1 minus I1 into R1, where R1, small r1 is the internal resistance of the electric cell of EMF E1, or comma VAC1 is equal to E1, because where R1, small r1 is the internal resistance of the cell of EMF E1. R1, small r1 is the internal resistance of the cell of EMF E1. And at this valence condition, when the galvanometer shows no deflection, provided the jockey J is pressed with the point C1, that means as the galvanometer shows no deflection, so I minus I1 will be equal to 0. That means no current will flow through the arm AE1C1 containing the cell of EMF E1. When the jockey J is pressed with the point C1 of the potentiometer where AB, galvanometer G, the galvanometer G shows no deflection. Galvanometer G shows no deflection and no current flows through that arm, and that's why I minus I1 will be 0. That means I minus I1 is the current which is flowing through the arm AE1C1, and I minus I1 will be 0 because galvanometer shows no deflection. That's why terminal voltage E1 minus I1 into R1 will be equal to E1 only, as I minus I1 equal 0. No current flows through that arm. Therefore, KL1 equal E1 according to the principle of potentiometer. According to the principle of potentiometer. According to the principle of potentiometer, we can say that potential difference across the portion AC1 of the potentiometer wire, that is VAC1, is equal KL1, where K is the potential gradient of the potentiometer wire AB. Potential gradient of the potentiometer wire AB. Potentiometer wire AB. Here VAC1 is equal to KL1. VAC1 equal to KL1. That means potential difference across the portion AC1 will be equal to KL1. That means potential difference across the portion AC1 is directly proportional to the length L1. Therefore, E1 equal KL1. E1 equal KL1, which is the EMF of the first electric cell, and which is equal to KL1. K is the potential gradient and L1 is the distance of the point C1 from A, at which galvanometer G shows no deflection. Now the plug is removed between the terminals 1 and 3, and plug is removed from the gap between the terminal 1 and 3 of two-way key, and the same plug is inserted in the gap between the terminals 2 and 3 of two-way key. The plug is inserted between 2 and 3 of two-way key, and the jockey J is pressed with the point C2. That means the jockey J is placed with the point C2 of potentiometer wire. The point C2 is at a distance L2 from the terminal A. And at this point, when the jockey J is touched with the point C2 of potentiometer wire AB, galvanometer G shows no deflection. And we can assume that current I prime flows through the arm AC2, but the current I minus I1 prime will be flowing through the arm AE2C2. When the jockey J is pressed with the point C2, galvanometer G shows no deflection again. Galvanometer G shows no deflection again when jockey J is pressed with the point C2. Now, as galvanometer shows no deflection, that's why the current I minus I1 prime will be equal 0. That means the current flowing through the arm AE2C2 will be 0. That means I minus I1 prime will be 0. Now, the plug is removed from the gap. Now the plug is removed from the gap between the terminals 1 and 3. The plug is removed from the gap between the terminals 1 and 3 and inserted in the gap between the terminals 2 and 3 of the two-way key. The plug is inserted in the gap between the terminals 2 and 3 of the two-way key so that the cell of E.m.f. E2 comes in the circuit. When the plug is inserted in the gap between the terminals 2 and 3 of the two-way key so that the cell of E.m.f. E2 comes in the circuit. When the jockey J is pressed with the point C2 of potentiometer wire the galvanometer, same galvanometer G shows no deflection. Same galvanometer G shows no deflection. At this balanced condition, E2 is equal KL2. That means potential difference across the arm AE2C2 will be equal to the potential difference across the portion AC2 of the potentiometer wire. We get E2 equal KL2. E2 equal K dot L2, where K is the potential gradient of the potentiometer wire. Dividing equation 1 by 2, we get E1 by E2. E1 by E2 as equal KL1 by KL2. E1 by E2 equal KL1 by KL2. Or E1 by E2 equal L1 by L2. E1 by E2 is equal L1 by L2. Ratio of two electric cells will be equal to the ratio of lengths at which galvanometer shows no deflection for the two electric cells E1 and E2 separately. In this way, using this above equation, the E.m.fs of the two electric cell can be compared. E.m.fs of the two electric cells can be compared. That means E.m.f. E1 of this electric cell is equal KL1, E1 equal KL1, and similarly E.m.f. of the second electric cell E2 will be equal to KL2. And we get E1 by E2 as equal L1 by L2. In this way, we can compare the E.m.fs of the two electric cells by using potentiometer. In the diagram, as L1 is greater than L2, that's why E1 by E2 will be greater than 1. Therefore, E1 is greater than E2. That means E.m.f. of the first electric cell will be greater than the E.m.f. of the second electric cell. When the jockey J is pressed with the point C1 of potentiometer wire, galvanometer shows no deflection and the point C1 is at a distance L1. When the same jockey J is pressed with the point C2, galvanometer shows no deflection and the point C2 is at a distance L2. As L1 is greater than L2, we can say that E1 will be greater than E2. EMF of the first electric cell will be greater than the EMF of the second electric cell. We can consider another additional information, that is E1 by E2 equal L1 by L2. Let E1 be the EMF. E1 be the EMF. E1 be the EMF of the unknown electric cell. And in that case, E1 equal L1 by L2 into E2. E1 equal L1 by L2 into E2. Thus, knowing the values of L1, L2 and E2, the EMF E1 of the unknown electric cell can be determined. The EMF E1 of the unknown electric cell can be determined. In the diagram, E2 is the EMF of the known electric cell. E2 is the known electric cell connected to the potentiometer where known electric cell. And also we can denote the unknown electric cell. E1 is the unknown electric cell. E1 is the unknown electric cell. In that case, we can find the EMF of the unknown electric cell E1 by knowing the lengths L1, L2 and E2. By knowing the values of L1, L2 and EMF E2, we can find the EMF of the known electric cell, because E1 equal L1 by L2 dot E2. Knowing the values of L1 and L2 and E2, we can find E1.